Welcome back. So in previous lecture we discussed about the movement of groundwater, where we learned that the groundwater, if with respect to the water table, if it moves closer to the surface, then it moves faster, whereas the deeper portion will have the groundwater movement will take more years, and to some extent it may take millennia. Like near to the surface it may take days, then years, then further deeper centuries, decades and millennia. Now few very important things, this we have already discussed in the previous lecture, so I'll just move ahead. So few important things about the groundwater bodies and reservoirs, which we will discuss now, mainly the aquifer, aquiclude, aquitard and all that, and how they have been defined and what are the material properties, mainly we will see that, and depending on the porosity and permeability, how they have been classified. So first, aquifer is porous and highly permeable. Example, sandstone. So if you define aquifer, then aquifer is defined in any lithological formation that not only stores but also transmit water at faster rate, and this is because the porosity is high and the permeability is also high. So porosity and permeability is high in aquifer, and it can transmit the water much faster than other layers. So if you remember, when we discussed about the shale bed, so shale bed is porous but less permeable. So those type of beds with the material similar to the shale, that is clay material, it will have low permeability, so it will not allow the water to pass through. But the aquifer will have high porosity and high permeability. So best example is, if you take the rock, then it is sandstone. Then coming to the next one, Aquiclude. So may contain water but does not transmit significant quantity. It is highly porous with low permeability. So example is shale, that what I was talking. So if you see the diagram here, it shows the location of water table. So water table is this one is the aquifer, and this is your water table. So potential water table has been considered with respect to its from the higher areas, and if you move to the lower grounds or in the foreland areas, then we will get the artesian well. But let us look at the boundaries between the different bodies, groundwater bodies. So aquifer, what we were talking about, a highly porous and highly permeable layer, which is confined between two aquicludes on the top and the bottom, and the aquiclude is high porosity and low permeability, so it will not allow the water to pass through. And we have also discussed about what is permeability, what do you mean by porosity and all that. And then we have the artesian well. So in next coming slides we will talk about the hydraulic gradient, and this is because of the hydraulic gradient that the well which is located in the downstream area or in the foreland will automatically flow without pumping the water. So mainly the artesian wells will be because of the hydraulic gradient. And also, if you have a structure like fault, then you will have an artesian well or artesian springs, we can say, along the fault, because the fault, the zone of shear zone will act as a conduit which will supply the groundwater, because if it is rupturing the aquifer, then it will supply the groundwater through and it acts as a conduit, the shear zone, and will result into the formation of the artesian springs. So Aquitard further is the formation with relatively no permeability. So you have low permeability, so it ranges between aquifer and aquiclude. So any layer which is having relatively low permeability, and it can be classified between aquifer and aquiclude. Example, the sediment size will be silt or silt plus clay, then it is termed as Aquitard. Then comes Aquifuge. Aquifuge is again mostly seen in rocks. For example, it is massive granite with some fractures and limestone, so it will have low porosity and low permeability. So this type of groundwater bodies are classified as Aquifuge. Now, confined and unconfined aquifer, if we take, then we have confined, unconfined aquifers not bounded by aquicludes. So as it has been seen in this figure, that you have the aquifer confined between two aquicludes. So unconfined will be not bounded by aquicludes. Confined will be bounded by aquicludes. So what the diagram shows here is the figure is the example of the confined aquifer. Then comes the perched aquifer. We'll see this example also of the perched aquifer. Usually occur at higher level compared to normal water table, and such aquifers which occurs at higher level compared to normal water table are termed as perched aquifers. Then artesian wells, as it has been shown here, artesian well as well as artesian spring are found as confined aquifer, governed by difference in pressure, and this difference in pressure is because of the hydraulic gradient. So this is the same diagram which you can go through, which talks about the different groundwater bodies: aquifer, aquiclude, artesian well, artesian spring, etc. Now another part, further we can discuss this, what we have discussed in the previous slide. A confined aquifer is situated between two aquicludes, and this is the bed of low, that is, aquiclude is a bed of low permeability. So we have the water table with respect to the upstream area, and the artesian well, that is, the flow of an artesian well is governed by difference in pressure, and this difference in pressure is caused because of the height of water table in recharge area, that is the upstream, and the height of top of the well in the low lying areas or the downstream area. So this difference in elevation, which has been shown here with respect to the water table in the upstream and the downstream, or upper reaches and down lower reaches, the difference in elevation will result into difference in pressure, and that will result into the flow of artesian well. And these are the between two aquiclude, we term this as a confined aquifer. Now if the well were as high as water table in the recharge area, there would be no pressure difference and thus no flow. So if the well is as high as water table, so in this case there won't be any water flow, but in the case of the lower reaches, you will find the formation of artesian. And this also, to some extent, what we are talking about the hydraulic gradient here, that is the difference between the height of the water table between the two wells in the upper reaches and the lower reaches. Now perched water table is, so one is it sits above the normal water table. So you have Aquiclude, and then you have a perched water table which separates the, so this is the perched water table which separates the perched water table and the lower main water table. So lower main water table is over here and the perched water table is over here. So it sits much higher than the main water table. So these are termed as perched water table, and this will occur mainly if you are having a body like Aquiclude and a porous body which is similar to the saturated zone here, then you may have the perched water table. Then groundwater and Darcy's law, what is the relation between this? We will quickly look at. So what we have here is the water table in the upper reaches and the lower reaches. So the height difference between these two and the distance of flow between the two wells and the amount of permeability what you will measure and then the area of flow. So if you have this information, you can calculate the discharge. So the speed of groundwater flow you can calculate based on hydraulic gradient, that is your Darcy's law, and it has been given as Q as hydraulic gradient is equal to A into the bracket K, which is permeability, H is the height difference, and L is the distance between the two wells. So based on this, we can talk about the hydraulic gradient. Now we will see if there is excess removal of groundwater, then what feature we will be able to envisage in terms of the water level and all that. So this is termed as cone of depression. So cone of depression, what we have the zones, like we have zone of aeration, zone of saturation, that is a west zone, and zone of saturation around the year. So this is the level of groundwater which will remain round the year, but during the wet seasons the zone of saturation will increase and will continue to supply water in dry season despite increased pumping rate and large cone depression is formed. So this is basically what will happen. The wet dry season you will have this water table, and dry or on another season round the year you will have this water table. So you have, and during the dry season the zone of aeration will increase and the water table will fall down, but you are having the pumping of the groundwater is through both the levels, that is the wet season water table and dry season water table. So excess removal of groundwater. So a well will supply water if it intersects the groundwater or water table. When water is pumped from a new well, the rate of withdrawal initially exceeds the rate of groundwater flow. So this imbalance in flow rate creates a conical depression in water table immediately surrounding the well, and it's called as cone of depression. So this cone of depression will be close to the well. So this is mainly because of excess removal of groundwater during dry season or during the wet season also, and that is because the influence by the inflow and outflow. The inflow is not so much, so that is the recharge. The recharge is slower than the removal of the groundwater. So this is a similar figure which talks about the influent and the outfluent streams. So this is an outfluent stream, whereas this is the influent stream in the upper reaches. And then we have different units which is resting over the rock, igneous rock. So we have confined aquifer, we have unconfined aquifer between the different layers, and of course it shows also the perched water table, which is above the normal water table, as we can see here. So this is the water table, and above the normal water table is the perched water table. So the interaction between surface and the groundwater, as we have discussed, that all recharge area where the infiltration will take place, and finally the recharge will supply the water through underground movement to the lower reaches. So idealized diagram showing some of the ways of surface and groundwater interaction in the landscape from mountain to sea or ocean. For example, the groundwater moves up along the fault. So this was what we were talking about, that when there is a flow from the upstream or the upper reaches, the fault will act as a conduit, and we will see the formation of springs or artesian springs along the fault to discharge as a spring and then seep into lakes and rivers in the plain areas, that is alluvial plain areas, deltas and beach. So this is very much similar to what is happening in India, that is in Himalayas and then Indo-Gangetic plain and the ocean. So interaction between the surface and groundwater further. So you have influent streams that loses water as it flows downstream, then water infiltrates into the ground, recharging the local groundwater because the water table is below the bottom of the stream channel. So whatever the water has been, there is a precipitation in the upstream, is infiltrated and passed on to the downstream channel. Then effluent stream which gets their water from the groundwater. So you refer the figure which I was showing in the previous slide, which will tell you the stream which gets the water from the groundwater is the effluent, and the influent stream which loses the water. So the surface of stream directly relates to the surface of groundwater. So the groundwater level or the water table is similar to the water table or the water level in the effluent stream, and the stream will rise and fall as the water table rises and falls. Then comes the Karst topography. Now the Karst topography we will also discuss, we will show some slides separately also, but it is a distinct topography in which the landscape is largely shaped by dissolution activities of the water and carbonates bedrock, usually the limestone, dolomites or marble. So these are some of the examples which talks about the dissolution activities. So example of the Karst topography, if you see, it looks something like this. Okay, so formation of the sinkholes. Now these sinkholes are because of the subsurface dissolution activity which has taken place underground and resulted into collapse of the surface material, resulting into the formation of sinkholes. Another example of Karst topography is seen mostly in the caves, and these are cave formation. So mainly the formation of cave, where you will see the formation of stalactites and stalagmites. So stalagmites are again column like features which are seen from ground towards, heading towards the sky, and whereas from the upper side coming towards the ground is your stalactites, and the stalagmite is from the ground. So this is again because of the flow of groundwater as well as the seepage from the surface. Water usage, if you take, then off-stream use, water that has been removed or diverted from the source is termed as off-stream use. Example, mostly the off-stream uses water for irrigation, thermoelectric power generation, industry processing, and public supply. Then second is water usage is consumptive use, type of upstream use in which water does not return to the stream, because in some of the irrigation plants or the thermoelectric power generation plants, the water will return back to the stream. But in case of the consumptivity usage, the stream or the groundwater resource, it will not return, it does not return to the stream or the groundwater resource immediately after the usage. Example is consumption by humans and animals. Then in-stream use, the water that is been used is not withdrawn from its resource. Example is use of water for navigation of vessels, hydroelectric power generation, fish and wildlife habitat and recreation. So these are the few examples of water usage. Further, if we look at, then maximum amount of water is been used for irrigation, that is 70%. For domestic use, it is hardly 10%, and 20% is by the industry. So global usage of water is 70% irrigation, 20% industry, and 10% for urban and rural homes. And trend of use in India, if you look at, then you have 73% is been used by irrigation, then comes domestic, industry, power, navigation, environment, economic, and evaporation. So this is the table which has been given, and also it has been projected that in future the demand is going to increase in terms of the irrigation. In 2050, the demand is going to be tremendously high. So this has been given by Ministry of Water Resource, which shows that the demand is ever increasing in terms of irrigation, in terms of drinking water, in terms of industry demand and other. So per capita this demand is going to increase. So per capita water availability in India, which you can see here with respect to the population. So expected increase in population is seen here in million by 2050, and then per capita availability will be this much. So it will be difficult for us to cope up with the demand. So it will reduce the demand the availability will reduce, whereas the demand will increase the population, because the population is going to increase to 2050. So the groundwater in northwest India or northern part, because this is what has been projected that how it is going to decrease. So from some of the examples which has been showed here is the aquifer conditions. So aquifer conditions in India, mainly where we have the good aquifer is the Indo-Gangetic plain. In the north and eastern India, they are the best, and in Gujarat, that is the Narmada and Tapti river alluvial plains or the coastal alluvium, these are the best aquifers which are available. Aquifers in the alluvium and limestone and sandstone are also been observed in central and southern India, because they don't have much of alluvium, but most of the aquifers are in the hard rocks, mainly the limestone and sandstone. Hard rock aquifer like basalt and others are seen again in the central India, and then those are mainly in the basement complexes like granite and gneiss and Deccan Traps, basalt mainly. So hard rock aquifer and metamorphic igneous rocks are been seen in the central part of the India. So this is again a diagram which shows the yield, potential yield of water, and this is in terms of the aquifer. Then groundwater depletion in northern India, analysis using GRACE data. So this information is important to understand that how there is a depletion of groundwater in northern India. So groundwater depletion in northern India. Now this analysis or the results which came in was through the GRACE satellite, and this is important for us when we are talking about the management of groundwater, because as we saw in the previous slides that the groundwater, the demand will increase, and if the demand will increase and if recharge is low, then we are going to lose the groundwater and there will be more crisis of water in our country. So in particularly the best aquifer or the aquifers which are available in India is the Indo-Gangetic plain, and that is our fertile land, the most fertile land on the continent. So the vast belt running east to west, the alluvial plains of the Indo-Gangetic or the Ganges and Brahmaputra river and other major rivers also hold the large amount of groundwater, and the usage, as we were talking about, who are the consumers. So consumer maximum 70% has been utilized for the irrigation, and so irrigation, what we are doing is some of the water has been siphoned through the canals on the surface, but most of the water throughout the year has been pumped from the groundwater. So the depletion was been experienced, and the depletion has been shown through the GRACE satellite analysis. So the groundwater in northern India is disappearing day by day. Rate of groundwater change has been determined based on observations from NASA's Gravity Recovery and Climate Experiment, that is the GRACE satellite. During the past decade, groundwater beneath the northern Indian states of Punjab, Haryana and Rajasthan has decreased by more than 88 million acre feet, that is 109 cubic kilometers. So this is the amount of depletion or the decrease in the groundwater in India, Indian state, basically Punjab, Haryana and Rajasthan. So groundwater levels have been declining by an average of 1 meter every 3 years. That is 1 feet per year. So this is the depletion which has been observed. Irrespective of very heavy rain, we have, so the irrespective of heavy rain, we have in Himalayas or the upper reaches, the recharge is very slow. So the groundwater level have been declining by an average 1 meter by every 3 years. So loss of groundwater is due to human activity, mainly the irrigation for cropland at faster rate than replenishments of aquifer can be natural process. So the recharge is, as I was talking, the recharge is slow and the consumption is much higher. So the recharge and the consumption, if they don't go side by side, then we are going to see the depletion in groundwater. So evolution of groundwater change, in order to, these are the changes which have been shown here, that we are having the depletion in the groundwater in this area mainly. So evolution of the groundwater change in northern India. So the red portion which you see here is showing the depletion of groundwater in the northern, or we can say Indo-Gangetic plains, and this is going to be very dangerous in terms of the future requirement which is projected either in 2025 or 2050, that is 2050. Evolution of the groundwater change in India using gray satellite, more than 109 cubic kilometer of groundwater disappeared between 2002 and 2008. So between 2002 to 2008, more than 100 cubic or 110 cubic kilometer groundwater disappeared. Reason for groundwater depletion in this area is mainly staggering population growth, rapid economic development, water hungry farmers. 95% of the groundwater is been used for irrigation, and of course if we are developing, then we need more and more water as a resource to develop more cities and develop more area. So urbanization is also consuming more and more water, and the water which is available on surface but excess requirement is sufficed by pumping the water out from the groundwater, and that is resulting into the depletion. So disappearing of such a large chunk of groundwater is mainly because of the population growth, rapid economic development and an irrigation purpose. So it occurred although there were no unusual trend in rainfall. In fact, rainfall was slightly above normal for the period which has been given above, but this is mainly because of the overconsumption, and this may lead to collapse of agricultural output and severe shortage of potable water for 114 million residents in the region. So the depletion will affect not only the population, that is the day-to-day requirement of by the people, but also the agricultural output. So the part of the water conservation, if we take, then we should improve certain things to have the better management of the groundwater. So, the improved agricultural practices, that is irrigation, could reduce water withdrawal by 20 to 30%. Then comes the engineering, technology and structure, that is the canals, which connects the rivers and siphoning the water to different areas for irrigation purposes. So, regulating irrigation and reducing evaporation, because while transferring water from river to canal through canals to different areas, you will have lot of evaporation also. Better technology in power plants and other industry. Less use of water due to improved efficiency. Water removal for thermoelectricity could be reduced as much as 20 to 30% by using cooling towers designed to use less or no water. Domestic use of water can be reduced at a relative low cost with more efficient bathrooms and sink fixtures, nighttime watering of lawns and gardens, and dripping irrigation system for domestic plants. Because we have in practice that we mostly open up the tap and allow the water to flow in our gardens and lawns, which can be reduced and can help in less consumption of groundwater. Then global water conservation, virtual water budgets. In some areas, like in our country, we do not charge the water, but in other countries the water is charged. So, whatever the water you use, that is cubic meters, cubic meter, the volume, you will have to pay for that water consumption. So, in India we do not charge, but if we start charging the water, then the consumption will definitely reduce, and better technology will also help us in less consumption of the groundwater or the water which is available with us, that is a potable water. So, water conservation virtual water budget, which has been shown here, that the input and the export. So, the amount of water necessary to produce a product such as home appliances or a crop such as wheat or coffee, figure shows virtual water balance and transfer in world. So, this will be the virtual water balance and transfer in the world in future, and at present also this is what we see. So, water management, need of water management, increasing demand of water, that is because of population, economic development, water supply problem in semi-arid and arid regions, water supply problem in megacities of humid region, water traded as commodity, capital market and regulation is not in proper order, factors need to be considered, natural factors, geological, geographical and climate, human factors, economic, social and political strategies, more surface water use in wet area, more groundwater use in dry area, reuse and recycle water on regular basis as well as during the emergencies. So, these are few tips which can reduce the water consumption and will have better management. Water and ecosystem. So, water resource development such as construction of dams, reservoirs, canals, aqueducts have a variety of environmental impacts at a variety of scales. Now, the example, that is the effect of dam on environment, what we usually faces in long term So land with its cultural and biological resources is lost in the area flooded by the reservoir. So this is the most common environmental effect or the impact of dam construction. Ecosystems are fragmented as migrating fish are blocked from moving upstream of the dam towards the hilltop areas with adjacent valleys are transformed to form isolated islands. So the overall ecosystem is disturbed. The reservoir trapped sediments that is transported from upstream by the rivers. It's been blocked close to the dam or the reservoir structure. The downstream hydrology and sediment transport system change the entire river environment, affecting the organism that lives there in the upstream and downstream area. So the hydrological cycle in terms of the water supply, if the dam has been constructed or any construction which has been done for the irrigation purposes, will to some extent will have major environmental impact, and that is on the ecosystem, biological resources, cultural resources, and also the sediments which has been yield has been blocked along the dam structure. So the downstream hydrology and sediment transport system changes the entire river environment, affecting the organism that lives there. So the problem is emerging global water shortage. Solution: control population growth and conserve water. Solution is possible, but it will take time and it will take a lot of proactive work. Thank you so much. I'll stop here.